Hello, this is Dr. Hanaa Assil, and today we're discussing the first chapter in Unit 2 of International AS Edexcel Chemistry, and this is about chemical energetics. So, let's remind ourselves what are exothermic and endothermic reactions. You should know that exothermic reaction is a reaction that gives out heat. Now, the reaction that gives out heat will give out heat to the surrounding solution. So the temperature of the surrounding solution will increase and the reaction will become hotter. You should realize that burning or combustion of any fuel is an exothermic reaction. Now, endothermic reactions is a reaction that takes in heat. Now, it takes in heat from what? It takes in heat from the surrounding solution. So that means that the surrounding solution will get colder or the temperature will decrease. So if he says that he did a reaction and the temperature went up, what type of reaction is this? This is an exothermic. If the reaction went down, it is an endothermic reaction. And then we can draw what we call a reaction profile diagram, and that indicates that the reactants at the beginning have a certain amount of energy. And then we said when they react, if this is an exothermic, we said exothermic means the reactants will lose energy or will lose heat or will give out heat, and that means that the products will have less energy than the reactants. Now, the difference in energy between the reactants and the products, this is what we call the delta H or enthalpy change or heat change. For exothermic reactions, the products have less energy than the reactants, and that means the delta H will have a negative value. And then we said, where is the activation energy? The activation energy is the minimum amount of energy needed to start the reaction. It is the difference in energy between the reactants and the top of that hill that we have. That is where you have the intermediate or what we call an activated complex. So the difference in energy between the reactants and the top, that is the activation energy. Now we include the activation energy if he's asking for a reaction profile, but if he's asking for an energy level diagram, we just show where reactants are, products are, and the difference between them is the delta H. Remember that if you're writing this kind of diagram for a specific equation, do not write the word reactants, products. You write what actually is reacting, whatever, hydrogen plus chlorine or whatever, and whatever the product is supposed to be, you actually write what that product is. Now, for an endothermic reaction, we said endothermic means that the reactants will take in heat, and that means that the product will have more energy than the reactants. The difference in energy between reactants and products is a delta H or enthalpy change. For the endothermic reaction, delta H is positive. Again, the activation energy is the difference in energy between the reactants and the top. And if we're writing an energy level diagram, you can just write the delta H without showing the energy of activation. Okay, now for the international AS or for the AS level, we're now going to talk about the delta H different types of enthalpy changes under standard conditions. So when you have a delta H with, this is a theta, a small O with a cross in the middle, that's called the theta. So this represents enthalpy change under standard conditions. Now, what are standard conditions? You should know that standard conditions are pressure is 1 atmosphere or 100 kilopascal or 100,000 pascal. That is the standard condition. Now, the temperature is the 298 degree Kelvin, which is the 25 degrees Celsius. And concentration, if we're talking about a solution, the standard condition for the concentration would be 1 mole per decimeter cubed. If we say that we're talking about a substance in its standard state, the standard state means the physical state under the standard conditions. Yeah, that means what is its state at 25 degrees centigrade and 1 atmosphere, which is the normal room temperature and pressure. Now, there are different types of enthalpy changes, and you are required to memorize the definition, or at least to understand so that you can write it, what each definition means. Well, we have something called standard enthalpy change of reaction. Now, if we say we're talking about the standard enthalpy change of reaction, it is the enthalpy change. Again, do you remember what enthalpy change means? It means heat change, or delta H. The enthalpy change that takes place when the amount of reactants shown in an equation react to give products under standard conditions, reactants and products in their standard state. Please be careful with the definition. When we are defining any of these standard enthalpy change of something, it is the enthalpy change that takes place when something happens under standard conditions, reactants and products in their standard state. So if we're talking about an enthalpy change of reaction, well, it is the enthalpy change that takes place when that reaction happens under standard conditions with reactants and products in their standard state. What if we're talking about standard enthalpy change of formation? Let's look at the definition. It is the enthalpy change that takes place when 1 mole of a compound in its standard state is formed from its constituent elements in their standard states under standard conditions. What does that mean? For example, if I'm trying to make methane, methane is CH4. Under standard conditions, that means under temperature of 25 degrees centigrade and pressure of 1 atmosphere, that's the normal conditions of the laboratory, methane is a gas. Now, if I'm talking about standard enthalpy change of formation, that means I'm talking about the enthalpy change that needs to make 1 mole of methane from its constituent elements. So what are the constituent elements of methane? Carbon and hydrogen in their standard state. So I have to start with carbon in its standard state, it's a solid. Hydrogen is a gas. So, and I'm trying to make 1 mole. So remember that when I balance this equation, it has to give 1 mole of methane. We do not use multiples. So this would be the equation for the standard enthalpy change of formation of methane. What about this one? Now, this equation is the formation of 1 mole of ethanol. So this would represent the enthalpy change that takes place when 1 mole of ethanol is formed from its constituent elements. Now, the standard state of ethanol is a liquid. Now, what elements do we use to make ethanol? We use carbon and hydrogen and oxygen. The state of carbon has to be a solid. Hydrogen is a gas, oxygen is a gas, and I balance it so that I give 1 mole of ethanol. I don't multiply through by 2. I don't say 4 carbon plus 6 hydrogen plus 1 oxygen to give 2 C2H5OH. No, I want the reaction to give 1 mole of the compound in its standard state, so ethanol as a liquid, formed from its constituent elements in their standard state, so carbon solid, hydrogen gas, oxygen gas, under standard conditions. Do you remember what the standard conditions were? Pressure is 1 atmosphere or 100 kilopascal. Temperature 298 degree Kelvin or 25 degrees Celsius. These are what we call the standard conditions. Now, keep in mind that the standard enthalpy change of formation for any element is 0. That's because I don't form carbon, for example. I don't form hydrogen. I form a compound. So this is the enthalpy change that takes place when 1 mole of a compound. But if I have an element, the delta H of formation for any element is 0. Another kind of enthalpy change that we need to know is the standard enthalpy change of combustion. You should know that this is the enthalpy change that takes place when 1 mole of a substance is burnt in excess oxygen under standard conditions, reactants and products being in their standard states. For example, if I have carbon plus oxygen to give carbon dioxide, This will be the equation for the standard enthalpy change of combustion of carbon, right? This is standard enthalpy change of combustion of carbon. The enthalpy change that takes place when 1 mole of a substance, so 1 mole of carbon, is burnt in excess oxygen under standard conditions or reactants and products in their standard state. So carbon is a solid, oxygen is a gas, carbon dioxide is a gas. Now, remember that you cannot burn water. You cannot burn oxygen. So remember that the enthalpy change of combustion for water is 0. Enthalpy change of combustion for oxygen is 0. So if I write this reaction, hydrogen plus oxygen to give water, this would be the reaction for delta H of what? Well, here this is a reaction in which you have burning of hydrogen to give water. So this is actually the reaction for the enthalpy change of combustion of hydrogen. But it's also something that forms 1 mole of water. So the delta H for this reaction would be also the delta H of formation of water. So you can have the same equation giving you. So if he gives you the delta H for that reaction, hydrogen plus half oxygen to give water, that is the delta H of combustion of hydrogen, and it is also the delta H of formation of water. Another kind of enthalpy change is standard enthalpy change of neutralization. Remember what was the reaction that we called neutralization? Reaction of acid with base to give salt plus water. So the standard enthalpy change of neutralization is the enthalpy change that takes place when 1 mole of water is formed by the reaction of an acid with an alkali under standard conditions. So for example, if I have sodium hydroxide plus hydrochloric acid, sodium hydroxide is an alkali plus hydrochloric acid to give the salt, sodium chloride plus water. But then when we wrote the ionic equation for this reaction, we ended up with H plus OH minus to give H2O. This was the ionic equation for any neutralization reaction. So we say that the standard enthalpy change of neutralization is the enthalpy change that takes place when 1 mole of water is formed by a reaction of an acid with an alkali under standard conditions. Another kind of enthalpy change is standard enthalpy change of atomization. Now, what is atomization? Atomization, first of all, this is the enthalpy change that takes place when 1 mole of gaseous atoms, pay attention to the gaseous, it has to be gaseous atoms formed from its elements under standard conditions. So for example, if I have iodine, iodine is I2 under standard conditions. That means 25 degrees Celsius and 1 atmosphere. Under normal laboratory conditions, it's a solid. So that is its standard condition. If I'm talking about standard enthalpy change of atomization, that means first I have to change the iodine to a gas and break it up into atoms. So instead of having I2, which is a diatomic molecule, I'm going to break this molecule to form atoms. Remember, that would mean that you need this amount of energy to break the bond between the two iodine and iodine atoms to form individual atoms in their gaseous state. Also, if I have Cl2 as a gas, I need to break it up. Of course, the standard condition of Cl2 is a gas. Now, standard enthalpy change of atomization would be the energy needed to change that into chlorine atoms in the gaseous state. Bromine, under its standard condition, is a liquid. Now, the energy needed to form atoms of bromine in the gaseous state, that would be the standard enthalpy change of atomization. Sodium in its standard state is a solid, it's a metal. The energy needed to change it into sodium gaseous atoms, that would be the enthalpy change of atomization. Okay, You should remember that bond energy is the enthalpy change required to break and separate 1 mole of bonds in the molecules of a gaseous element or compound. So if I have hydrogen plus chlorine to give to HCl, what do we have? We have a bond between H and H. We have a bond between Cl and Cl. And we have 2 HCl bonds that are formed. Now, each of these bonds needs a certain amount of energy to be broken or to be formed. This is called the bond energy. So the hydrogen-hydrogen bond, he gives you these numbers. You're not required to memorize them. So from what he gives me, we have found out that to break the HH bond, I need to give it 436 kilocalories or kilojoules. To break the Cl-Cl bond, I need to give it 242. So remember that the breaking of bonds in reactants, we need to add energy. It is an endothermic process. Now, when bonds are formed in the products, they release energy. So he's saying that each HCl will release 431. I have 2 HCl bonds that will be formed, so that will release 862 kilojoules. Addition of energy is positive, release of energy is negative. Now, to get the overall delta H, in order to calculate the overall delta H, we have the energy needed to break the bonds in a positive number minus the energy released when the bonds are formed in the products. Overall here, for example, the answer is a negative number, and that tells me that overall this reaction is exothermic. Okay, why is it exothermic? Because heat is lost to the environment. If it's a negative number, that means heat is given out to the environment. Remember that the bond energy is actually an indication of the strength of the bond. So the stronger the bond, the more energy it needs to be broken. And you should also realize that the shorter the bond, the stronger it is. So a bond is shorter if it is a double bond, for example. You should realize that covalent bonds are very strong. They will need a lot of energy to be broken. We will talk about what is hydrogen bonds, but for now, just remember that covalent bonds are stronger and need more energy to be broken than hydrogen bonds, and these will need more energy to be broken than the van der Waals forces. The van der Waals forces were the weak forces between molecules, the weak attraction forces between molecules that we were saying for a covalent compound to melt, for example, I need to break the weak attraction forces between the molecules. These are called van der Waals forces, so these need a very small amount of energy. Now, we said the shorter the bond, the stronger it is. Remember that a double bond between carbons is shorter than a single bond, so it will need more energy to be broken than the single bond. An HCl bond is stronger than an HI bond. This is because when we talk about chlorine, bromine, iodine, the chlorine is a smaller molecule, so there is stronger attraction forces between the positive nucleus of the atoms and the bonding pair of electrons. For HI, the iodine is a large atom, so there is weaker attraction forces between its nucleus and the bonding pair of electrons. So the HCl will need more energy to be broken than the HI. So let's take a look at this example. He gives me bond energies and he wants me to determine what is the delta H for this reaction. So let's look at these reactions. Nitrogen, you should realize that between these two nitrogens, we have a triple bond. And he's telling me that to break the triple bond, I need 941 kilojoules. Now I have 3 HH bonds, and he's telling me I need 436 kilojoules to break these bonds. The NH bonds, each NH bond needs 391, but how many do we have? He's telling me I have 2 ammonias. Each ammonia has 3 NH bonds. So actually I have a total of 6 NH bonds. So to calculate the delta H, the energy needed to break the NN bond plus the energy needed to break the 3 hydrogen bonds, and then minus the energy that is given off when the 6 NH bonds are formed. The overall is a negative number, and that tells me that the reaction is exothermic. This is another example. Please pay attention to what is happening to the bonds. So here he has a reaction. He's telling me calculate the molar enthalpy change. That is the delta H. Okay, we said that bonds in the reactants, we need to break them, we add energy. Bonds in the products are formed, so they give out energy. They release energy, so that's a negative. So the ones in the reactants are positive. The energy from the products is a negative number. So let's take a look. The energy that I need to give this reaction in order to break the bonds in the reactants. Well, I have 4 CH bonds, and he tells me that each CH bond needs 412. Plus, I have 2 oxygen-oxygen bonds, and he says that each of them needs 496, so it is 2 times 496. This overall is the amount of energy that I need to give in a positive number to the reaction in order to break the bonds in the reactant. Now, in the products, what am I forming? I'm forming 2 CO bonds. Can you see the C double bond O? I have a C double bond O on this end and a C double. We're looking at the bonds, not the atoms. So how many C double bond O do I have? I have 2. And he's telling me each one is 743. Plus the OH bond, each OH bond, when it forms, it will give 463. Now, how many OH bonds do I have? He's telling me I have 2 water. Each water has 2 OH bonds. So that's a total of 4, and that means that this is the amount of energy released. Now, to get delta H, you do reactants minus products. This comes out as a negative number. So that is one way of determining delta H, when he gives you bond energies and he says calculate delta H. But in other cases, he will say he did a reaction in a calorimeter like this, and he measured initial temperature and final temperature, and he's telling me to calculate delta H. So in this case, I'm going to use these equations. So if we do a reaction, and he says at the beginning I had a certain temperature, at the end I had another temperature. So I first of all calculate Q. Q is the amount of energy or quantity of energy. Now, how do we calculate that? It is the mass of the solution. I'm going to remind you that a solution is mostly water. The density of water is 1. So for a solution, the mass is the same as the volume. So if he says mass of solution is the same as its volume, if I say I have 25 centimeter cubed of a solution, that means I have 25 grams of the solution. So M is the mass. C is a specific heat capacity. This is a constant number. So whenever we see C, we're going to put 4.18. And the delta T is the temperature change. Now, once we have calculated Q, then we will need to calculate delta H. Delta H is the Q over the number of moles. If you remember from chemical calculations, how we calculated the number of moles, depending on the information he gives me, whether it's mass over molecular mass or concentration times volume, and so on. And remember, delta H will need to have a sign. So let's try this question. This says, find the enthalpy change for this reaction when excess magnesium is added to 100 centimeter cubed of 2 mole per decimeter cubed copper sulfate solution. The temperature rises from 20 to 65. So we said, in order to calculate the enthalpy change, I need to calculate Q first. We said, how do we calculate Q? It is mc delta T. M is the mass of the solution. Where is the mass of the solution? He said he used 100 centimeter cubed. That means 100 grams. Times C, we said C is always 4.18. Times the difference in temperatures, 65 minus 20. That comes out to be a number in joules. Remember that the number that comes out for Q from this equation is in joules. Usually it's a big number. So if we divide it by 1,000, then the answer is in kilojoules. Then I need to calculate delta H. Well, delta H is Q over N, so I need to calculate N. Now, how do I calculate N for this reaction? Well, what information do I have? He's talking about copper sulfate solution. He's giving me volume and concentration. So I use the equation that says number of moles is concentration times volume. So that is the 2 times, remember, if the volume is in centimeter cubed, you need to divide it by 1,000 before you put it into this equation. So this is 0.2 moles of copper sulfate. And that means to get delta H, I divide Q over N. But then the number that comes out must have a sign. Now, should I put the delta H in a positive number or a negative number? How do I know? We said if it is positive, it's endo. If it is negative, it is exo. Is this reaction endothermic or exothermic? How do we determine that? We look at what happened to the temperature. He's telling me the temperature rises from 20 to 65. That means the reaction became hotter. That means this is an exothermic reaction. That means delta H is a negative number. So I have to put the minus sign before 94 kilojoule per mole. This is another question where he said he did a titration and he did volume of potassium hydroxide is 25 centimeter cubed, and he has a starting temperature, and then the volume of acid added in the titration is 25 centimeter cubed, and the highest temperature reached was this. Calculate the heat energy or the quantity of heat. Well, he's telling me the equation. If he doesn't tell me the equation, I have to know that it is mc delta T. What is m? Remember we said m is the volume of the solution, which is the same as the mass of the solution. Now, what is the mass of the solution? Well, what did he do? He added 25 centimeter cubed of potassium hydroxide to 25 centimeter cubed of acid. So the total mass of the solution is 50. The delta T is the difference in temperature. So Q will be the mass times 4.18 times the change in temperature. So that comes out in joules. This is another reaction where he says the student uses this apparatus to measure the temperature change when solid sodium hydrogen carbonate is added. And he says use a measuring cylinder to add 35 centimeter cubed of 1 mole per decimeter cubed of citric acid. He recorded the initial temperature. He added 7 grams of sodium hydrogen carbonate, and he stirred the reaction. Now, the initial temperature is this, and the lowest temperature is this. Show that the heat energy is about 2500. Well, to calculate Q, I need mc delta T. What is m? Let's go back. What is m? M is the mass of the solution. What is the mass of the solution? Well, I have 35 centimeter cubed of citric acid. That means the M is 35. And the difference in temperature, we calculate the difference. And that means my M is this number in joules, which is about 2500. Then he says, calculate the enthalpy change for the reaction. So how do I get delta H of citric acid? Again, what does he tell me? He says I have a certain concentration and a certain volume, so I multiply that and get the number of moles. And then I get delta H is Q over N. Are we going to put a positive or a negative for delta H? You should realize that the initial temperature is 21. The lowest temperature is 4. That means temperature went down. That means your final answer must be a positive number. Okay? Okay, remember that the value of delta H that is calculated using this kind of calculation is usually different from the actual delta H. And if he says why, this is because usually when we do this experiment, there is heat lost to the environment. Sometimes we have incomplete combustion if we're trying to burn a fuel, incomplete transfer of heat. Some of the fuel may evaporate, so our mass is different in mass, so something would be different, and some of the heat is absorbed by the apparatus itself, which we call the calorimeter. Sometimes, if we're not measuring them under standard conditions, then the equations should not apply and we get a wrong answer. Okay, now another method of getting the delta H would be through Hess's law. And Hess's law says the total enthalpy change in a reaction is independent of the route by which the chemical reaction takes place as long as the initial and final conditions are the same. What does that mean? I have reactants in A. I'm trying to react them to form B. Do we understand that? Now, how am I going to change A to B? Well, I can use a certain reaction, which we call route 1. And I can use a different method, which we're going to call route 2. And what Hess's law says is that the total enthalpy change for route 1 should be the same as the enthalpy change for route 2. Because once you're starting with the same thing and ending with the same thing, you should have the same enthalpy change. So he will then give you a reaction and he will give you some information. And this information is either the delta H of combustion for each of these or the delta H of formation for each of these. So here he's telling me I have carbon plus 2 hydrogen to give methane. And he gives me the information that delta H of combustion of carbon, that means if I burn carbon in oxygen, it will give out 394 kilojoules. If I burn 1 mole of hydrogen, it will give out 286. If I burn 1 mole of methane, it will give 890. Now he wants the overall delta H, and that means that I have two pathways. Either I'm going carbon plus 2 hydrogen to give methane, or I'm going from carbon and hydrogen and I'm burning each of these. So if I burn carbon, it gives carbon dioxide. If I burn 2 hydrogen, it will give 2 water. If I burn the methane, it gives carbon dioxide plus water. So going from carbon plus hydrogen to give carbon dioxide plus water. Can you see where I'm going? Carbon plus hydrogen to give carbon dioxide plus water. How can I go? I can either go with the green arrow, carbon plus hydrogen to give methane, and then burn the methane to give carbon dioxide plus water. Or I go directly and burn carbon plus hydrogen to give carbon dioxide and water. Now, the route, the green arrow, the total delta H following the green arrow should be the same as the delta H following the red arrow. That means the delta H of the reaction that he's given me, carbon plus hydrogen to give methane, the delta H for that reaction, plus the amount of delta H combustion of methane should be equal to the burning of carbon plus the burning of 2 hydrogens. Can you see what we're doing? He said burning of carbon to give carbon dioxide will release minus 394. And then 1 mole of hydrogen gives minus 286. I have 2 moles. So going with the red arrow, the delta H is minus 394 plus 2 times minus 286. But going the other way around, carbon plus hydrogen to give methane and then burning methane to give carbon dioxide and water, I have delta H plus the minus 890 for the burning of methane. So the delta H plus the minus 890 is equal to the ones on the other side. Now, from that equation, I can calculate for delta H, and from that reaction, the delta H is minus 76. Do we understand that? So if he gives information about the enthalpy change for combustion, I draw the arrows going down. Burning carbon, burning hydrogen, burning methane, going down to form carbon dioxide plus water. But if he gives me this kind of reaction and he gives information about the delta H of formation, that means he's telling me to form C2H6, it is minus 85. To form 1 mole of CO2, it's minus 394. To form 1 mole of water, it's 286. What about the delta H of formation of oxygen? He did not give me the delta H of formation of oxygen. Well, we said delta H of formation of any element is 0. So I don't have delta H of formation for oxygen. And delta H of formation means my arrows go up. I am forming each of these things from its elements. So which elements do I have? I have the C2H6 was made from 2 carbon. The 6 hydrogens was made from 3H2. The O2 was made from 3.5 O2. So the box down will give you the elements and my arrows go up. Now, where are my pathways? Well, what am I trying to do? Either I go from the lower box, 2 carbon plus 3.5 oxygen plus 3H2, to form at the end 2 CO2 plus 3 water. Or I go directly to give 2 CO2 plus 3 water. So the green arrow, delta H plus the formations of C2H6 will be equal to the formations of CO2 and 3 water. I have 2 CO2s and I have 3 water. This is the equation, and that means I can solve for delta H. Please try these questions so that you can understand them a little bit better. Okay, thank you for listening, and I hope this will be better, and we will be doing another video on some questions and answers on this chapter. Thank you for listening.